In the previous video, we learned how to assign oxidation numbers. Here we're going to see how to put those oxidation numbers to work. Specifically, our end goal is to figure out who's being oxidized and who's being reduced in a redox reaction. The acronym OIL-RIG could be really helpful when you're doing these types of problems. So oil oxidation is loss, and it's specifically the loss of electrons. Reduction is the gain of electrons. So that's the RIG portion of that acronym, OIL-RIG. First step, and it's part A of the problem, is to assign oxidation numbers. So that's, again, like what you were doing in the previous set of problems. So zinc is completely by itself, and it doesn't have a charge. It's a single thing. So it has an oxidation number of 0. Here with the silver oxide, I'm going to split it in half. I always do my oxygens first. So I'll do -2 on the oxygen. It's a neutral compound, so it has to add up to 0. The oxidation numbers have to add up to 0. So if it's a -2 on this side, there's only one oxygen, then I'm going to do a +2 on that side. But there's 2 silvers that share that +2. So individually, they're both +1. So I'm going to do +1 times 2 gives me +2. Come over here. There's 1 zinc and 1 oxygen. So since it has to equal 0, I know that my zinc is going to be a +2. My oxygen is going to be a -2. Again, be on the lookout. It's a common mistake. People think, oh, silver, it's going to be a +1 because that's what they've memorized from the nomenclature section. But if anything is by itself and it doesn't have a charge, then it has an oxidation number of 0. Think about the fact that it's neutral. Alright, so once you're done with that, then you can start analyzing what's going on. So I see that our zinc started out at 0. And then on the product side, it went to +2. So that tells me, because it became positive, it went from 0 and it went to +2. Whenever you go in the positive direction, positive to lose, that zinc lost 2 electrons. In these problems, something always has to lose and something always has to gain. The electrons have to go somewhere. So as I'm analyzing, the next thing I'm going to analyze is my silver, because it starts as a +1. So the silver in silver oxide started as a +1, and then on the product side, it went to a 0. So it went in the negative direction on the number line. So this means that silver specifically gained 1 electron. And I know that could be a point of confusion, so let me just do a little picture to help us remember. If you have a number line, 0, +1, +2, we'll do -1, -2. If something goes in this direction, so it starts as a -1, it turns into a +1 or whatever. If it goes to the more positive, this means it lost electrons. And if it started anywhere on the right and moved to the left, that tells us that it gained electrons. So any kind, becoming more negative means that it gained electrons. All right, maybe that can help a little bit as we're going through these problems. So which species is oxidized? Oxidation is loss. So I go back up here to my analysis and I can tell that zinc was oxidized. And which species is reduced? Reduction is gain. And that means that the silver in the silver oxide, different ALEX questions, different homework questions ask for different ways. I'll be very specific if I ask you this question, but sometimes they want you to just report the silver, and sometimes they want the whole compound. So definitely look at their explanations of what they want. But as long as you recognize that the silver is the one that's gaining as the reaction proceeds. All right, so the agents are opposites, and I always think of like James Bond or something. He's like a double agent. You think he's representing something, but he's actually representing something else. So agents are opposites. So since zinc is being oxidized, that tells us that zinc is our reducing agent. And likewise, silver is being reduced, or the silver oxide is being reduced. Therefore, that's our oxidizing agent. It flip-flops for the agents. The oil rig applies to your initial analysis, and then you flip that for the agents. How many electrons are transferred? This is a really important part of this because we need to follow the law of conservation of mass. Somebody can't just lose electrons and we never know where they went. So it's kind of problematic the way we wrote it. Zinc lost 2, but silver only gained 1. I mean, that doesn't make sense. Where did that other one go? So when we're approaching this last one, we want to think about the coefficients. So I usually just look at the coefficients on the reactant side. So we have a 1 here and a 1 here. So if I'm balancing this, I'm like, okay, I have 1 zinc. So this whole process of losing electrons happened for 1 mole of zinc. So still I would do 1, the coefficient, times 2 electrons, and I get 2 electrons. For silver though, I have a coefficient of 1, but there's 2 silver atoms, or 2 moles of silver. So I want to think of silver as being twice as much. So even though it gained 1 electron, there's 2 silver, and they each gained 1 electron, so there I have 2 electrons. These numbers, when you start doing this analysis, they need to match. The amount lost has to equal the amount gained. So when we go to answer this, how many electrons are transferred? The answer is 2 electrons. Students always ask me, well, why isn't it 4? Think about the definition of transfer. If someone transfers money into your bank account, maybe they transfer $50, right? So their bank account goes down by $50 and your bank account goes up by $50. They lost 50, you gained 50, but you don't say 100 was transferred, you just say $50 were transferred. So it's the same kind of idea here. Somebody lost, somebody gained. We want the 2 numbers to be equal. We want to make sure nobody's stealing our money. We want to make sure, we know where the electrons are going. So we just go with the single value, the 2. We don't add them or anything. Alrighty, our first step when we do these problems is to assign the oxidation numbers. Aluminum is by itself and it's neutral, so it'll have an oxidation number of 0. When we have coefficients, we ignore them until we get to part D about how many electrons are transferred. So in the assignment of the oxidation number, I see I have silver, it's by itself, it has a +1 charge. So I'm going to do a +1 oxidation number. Aluminum ion has a +3 charge and it's just a single thing, so the oxidation number will be the same. Ignoring the coefficient, I see I have a neutral single species, so the oxidation number would just be 0. Aluminum goes from 0 on the left to +3 on the right. Therefore, it lost 3 electrons. It moved in the positive direction. Silver ion started as a +1 and went down to a 0 on the product side. Therefore, it gained 1 electron. Which species is oxidized? Oxidation is loss, so that's going to be my aluminum. And then which species is reduced? That's going to be my silver ion because it gained an electron. Agents are opposites, so my aluminum is the reducing agent And since silver was reduced, the silver ion was reduced, it serves as my oxidizing agent. Last step here, analyzing the number of electrons that are transferred. So the same kind of value that you would use if you're balancing. So you're like, how many aluminums do I have? You consider the coefficient and the subscript. So if you're balancing, you tell me, I just have one aluminum. So 1 times 3 gives me 3 electrons. If you're balancing, and I asked you about silver, you'd see this coefficient and you'd say, I have 3 silvers. So we're going to do 3 times 1, and that's going to give me 3 electrons. Remember, those two numbers need to match. If they don't, then try again. Erase your work and try it again. But therefore, I know I have 3 electrons transferred because they do match. Let's start by signing our oxidation numbers. We ignore the coefficients. So I'll do a 0 on aluminum because it's by itself and it's neutral. Tin has a +2 charge, so that'll be its oxidation number because it's by itself. Over here we have an aluminum ion, so we'll do a +3. Again, I'm covering up the coefficients because I'm ignoring them during the assignment of the oxidation numbers. Neutral by itself, just a single thing, it's going to be a 0. So in my analysis, aluminum went from 0 to +3. That means it lost 3 electrons. Tin started out as a +2 and then went to 0. That means it gained 2 electrons. Oxidation is loss, so aluminum was oxidized. Reduction is gain, so that tin ion was reduced. That makes aluminum my reducing agent and the tin ion the oxidizing agent. Let's just fix the electrons, figure out what's going on with our electrons. So aluminum has a coefficient of 2, and there's just 2 of them. So then I do 2 times 3, and that gives me 6 electrons. Tin has a coefficient of 3, so it's 3 times 2, and that gives me 6 electrons. So 6 electrons are transferred. All right, let's start by assigning the oxidation numbers. So I have neutral solid aluminum. I'm going to ignore that coefficient, and I'm going to give it an oxidation number of 0. This is diatomic oxygen, but it's still by itself. And it's neutral. It's just a single thing. I'm ignoring the coefficient, and I'm going to do a 0. Remember, you always have to do 0 on your diatomic elemental gases. Here, we're going to ignore the coefficient, but we're going to take the approach of splitting this in half. It's neutral, so everything internally has to add up to 0. I'm going to give the oxygen a -2 assignment because it's in a compound. And then I'll do -2 times 3. That gives me -6. So on this side, I need a +6 to get to that 0. There's 2 aluminums, however. And so individually, I can surmise that they'd both be +3 because I'll do 2 times +3 equals +6. 3 times -2 equals -6. And then +6 minus 6 equals the overall charge on the compound. I'm glad this example came up because when we're doing our analysis, we want to look at the circled values. So right now, we're going to ignore this +6 and the -6. It's just our work or a means to an end. We don't have to use them anymore. So I'm going to say that aluminum started at 0 and went to +3. It lost 3 electrons. An oxygen gas started at a 0 and went to a -2. It gained 2 electrons. Oxidation is loss. Reduction is gain. And our agents are the opposite to that. How many electrons are transferred? Again, think about it in the same way that you would when you're balancing. How many aluminums do I have on the reactant side? Well, I have a coefficient of 4, so I'm going to put a 4 here. 4 times 3 gives me 12 electrons. Oxygen is a little bit trickier. If I was balancing it, I have to consider both the coefficient and the subscript. So I'm going to do 3 times 2 on this. I have 6 oxygens. So 6 times 2 gives me 12. And that'll be our answer down here. Alrighty, on to the next page. This is 12A. Even though it wasn't set up the same way as the problems on the previous page, I do like this format, and it's pretty typical of what you'll be asked when you're asked to analyze a redox reaction. So I'll keep it the same for these two. Ignoring the coefficient, I'm going to do a 0 on my lithium. It's a neutral solid compound. Same thing here. Be careful with those diatomic compounds. If they're just one thing, then it's going to be a 0. Ignoring the coefficient, I feel really comfortable doing a -1 on my chlorine. It's neutral, it has to equal 0, which tells me the lithium is a +1. There's one of each of them. Alrighty, so for our analysis here, I'm going to start with lithium. Lithium goes from 0 on the left to +1 on the right. That means it lost 1 electron. The diatomic chlorine goes from 0 on the left to -1 on the right, so then it gained 1 electron. It became more negative, so it gained. Oxidized is lost, so I'm going to put lithium as being oxidized and as being my reducing agent. The chlorine gained electrons, the diatomic chlorine, so that will be reduced, and that will also be my oxidizing agent. So it might be really tempting. We have a loss of 1 electron and a gain of 1 electron. To put 1 electron down here, I encourage you to always check those coefficients. So what you're going to see here is that you have 2 lithiums. So you have to multiply this thing by 2. And then you have diatomic chlorine, so there's 2 chlorines. So 2 times 1 is 2. So the answer down here is actually 2. So we have another synthesis reaction. And synthesis, as a reminder, occurs when multiple things come together to create a product. So things have been combined, and sometimes we call them combination reactions. Nonetheless, I still have to assign my oxidation numbers. Neutral, solid carbon. Diatomic oxygen always gets a 0. -2. -2 times 2 gives me a -4. That means my carbon is a +4. There's just one of them, so the entire +4 belongs to that individual carbon. Carbon went from 0 to +4. That means it lost 4 electrons. Oxidation is lost. So I'll put carbon as my species that was oxidized and as my reducing agent. oxygen went from 0 to -2. It gained 2 electrons. Reduction is gained, making oxygen gas my oxidizing agent. Now to figure out what's going on with my electrons, there's only one carbon, so I'll do 1 times 4. There's 2 oxygens, it's diatomic, so I'll do 2 times 2, and that'll give me 4. Numbers match, so I'm confident that that's the number of electrons that were transferred. Alrighty, so classifying reactions is no easy task. We want to look for certain clues, but when those clues aren't there, our only option is to assign oxidation numbers and try to figure out if there is a change in oxidation numbers. Let me go through some examples. I think it'll make a little bit more sense. So this reaction's all over the place. I don't really necessarily see it as being a combination or decomposition. I don't see those telltale clues. So my only option then is to assign oxidation numbers. So I'm going to split this in half, and this is going to equal 0, and I'll do a -2 for my oxygen. -2 times 3 is -6. Then I'm going to have a +6 over there that's shared between the 2 irons. So 2 times +3 gives me +6. 3 times -2 gives me -6. +6 and -6 add up to 0. Ignore those coefficients. I'm going to do a -2 on my oxygen and a +2 on my carbon. It's neutral, so that'll add up to 0 for us. Finally, a more straightforward one. It's a neutral single compound, so I'll do a 0. Ignoring the coefficients on the carbon dioxide, I'm going to do a -2 on the oxygen. -2 times 2 is -4. I need a +4 on this side, and there's just one carbon, so I'll do a +4. So 1 times +4 is +4. 2 times -2 is -4. +4 and -4 add up to 0. You want to check the ones that change from left to right. So I systematically go through everything and just see what's going on. So iron is the first thing I run into. Iron started at a +3 and went to a 0. So +3 to 0, that means it gained electrons. It moved to the left on the number line, it gained electrons. Oxygen. Oxygen is a -2, a -2, a -2. Boring. It stayed as a -2 throughout the whole thing. Don't write it down. Carbon started at a +2 on the left and turned into a +4 on the right. And it went in a positive direction. So that means it lost specifically 2 electrons, and the iron gained 3. So we have something that's gaining electrons and something that's losing electrons. We have reduction and oxidation occurring in this reaction. So therefore, we're able to classify this as a redox reaction. Alrighty, let's look at this second one. This one has some things that I'm recognizing. So we have some kind of fuel here, a hydrocarbon fuel. So something that's carbon, hydrogen, or oxygen. And then I have oxygen gas, and I'm producing carbon dioxide and water. So these species right here, the oxygen gas and then carbon dioxide and water on the product side, that's a pattern that you need to memorize, right? That's the pattern for combustion when we burn something. The good news is we could assign oxidation numbers to all of these species. We don't need to do. We don't need to do that. Combustion is always also a redox reaction. So if you know it's combustion, then you also know that it's a redox reaction. And we're identifying its combustion by the pattern of reactants and products, the ones that I boxed. Alrighty, on this next one. Again, it looks so complicated. It's not jumping out at me as being like a combination or decomposition or one of those ones that I think are a little bit easier to recognize. So then I'm only left with one option, which is to see if it's redox. Ooh, so we haven't seen this in a little bit. When we're assigning the oxidation numbers and we got a parentheses, we have to undo the parentheses. So I'm going to give the 3 back to the aluminum. So I know aluminum's a +3, and then hydroxide is a -1. So undo your crisscross if you have parentheses. So my oxidation numbers will be +3 on my aluminum. I'll split this in half. It has to equal -1. So it's a -2 on the oxygen and a +1 on the hydrogen. Ignore your coefficient. We have a hydrogen that's a +1. Ignore our coefficient. Chloride by itself is a -1. Aluminum, +3. Chloride, -1. Water, it's a neutral compound, has to equal 0. I'll do a -2 on my oxygen, +1 on my hydrogen. 2 times +1 gives me +2. 1 times -2 gives me a -2. These add up to 0. Look at all your circled values. Let's systematically look at them. Aluminum was a +3 over here and a +3 over here. So it didn't gain or lose electrons. Oxygen is a -2 and a -2. Nothing going on with our oxygen. Hydrogen, lots of hydrogens, but every single one of the hydrogens are +1s. And then our chloride is a -1 over here and a -1 over here. Also nothing going on with that chlorine or chloride. So I can't classify this as a redox reaction. This is a super tricky one, and I wouldn't do this to you guys, especially at this point. But eventually you're gonna see, and I'll make them more apparent if I do ask you about them. Eventually you'll see you have a hydroxide, and in a previous lecture we talked about how hydroxides are associated with bases. And then you have H+, those protons that are associated with acids. So we have something that's a base and something that's an acid, and then over here we form water, which means officially this, if you had to classify it, it would be an acid-base neutralization reaction.